This isn't some inhospitable mountainous region, nor is it a monster from outer space. It's wood. Now what about this? No, not wood again. It's paper. And this? Not some dense tropical jungle, and it's not spaghetti either. It's cloth. But wood, paper and cloth aren't the only things we can look at very closely. Animals too reveal some of their smallest secrets when they're viewed through the microscope. Even something as ordinary as a fly looks quite fantastic when it's seen in all its detail. The amazingly complex head and the huge compound eyes, each eye made up of hundreds of small individual parts. And this isn't part of the moon's surface, but skin, human skin. But microscope pictures haven't always been as clear as those. It's taken 300 years to develop a microscope that can give us pictures like that. So let's go back to the beginning of the story. Let's look at why we need a microscope at all. At the moment, I'm a long way away from you, about 20 meters, so I look small and it's difficult for you to see anything of me in detail. But as I get closer, I get bigger. Of course, I haven't actually grown, I'm still the same size. But because I'm nearer, I appear to be bigger, and you can see more detail. This button, for example, or my necklace. If I want to show you even more detail, all I have to do is to step closer and closer. But now you can see there's a problem. If we get really close to things, they get fuzzy, they get out of focus. If we want to look at things really closely, we have to use a tool, a magnifying glass. And this helps us to look at things really closely without them going out of focus. Here's our fly again. It's so small that it's very difficult to see. And if we move in closer to see more detail, it goes fuzzy, it goes out of focus. But put in the magnifying glass, and it's in focus. And because we're looking at it more closely, it looks bigger. We can see more of the detail. Pieces of glass like this, which help us to look at things more closely and make them look bigger, are called lenses. Because lenses make things look bigger than they really are, we say they magnify. Now, let's look more closely at a lens. Each face, each side of the lens has to be curved. And if we want to get more magnification, to look at things more closely, to make them look even bigger, each face has to be more curved and more curved. Let's see what our fly looks like through a sphere like this. Well, the fly certainly looks much bigger than it did through the magnifying glass, but it's not the right shape, it's distorted. The more a lens magnifies something, the more it distorts it. To find out more about distortion, let's do a test. We're using this test drawing because we know exactly what it should look like. Now, through the lens, you can see very clearly the kind of distortion that occurs. But notice the square in the middle. It's hardly distorted at all. And that's our clue for finding a way round the problem. We use just the middle part of the lens. Now let's look at our fly through just the middle part of the sphere. Although we can't see all the fly, what we can see isn't distorted. Now, if we want to get even bigger magnification, then we have to use a smaller sphere. A smaller sphere is more curved, so it magnifies more. The smaller the sphere, the bigger the magnification. But very small spheres are very difficult to make. To make a good lens, the glass has to be ground into shape and polished so that it's perfectly smooth. Even with modern machines it's a difficult job, but despite the difficulties, that's exactly what this man did. Antony van Leeuwenhoek, a Dutchman, lived over 300 years ago, yet he was able to make microscopes using very small lenses, which he mounted like this in a special holder. This is a copy of one of the first microscopes ever made. Leeuwenhoek had to make a new holder for each new lens, and each lens he carefully ground and polished himself. You can imagine how difficult it was for him. This is the lens. It's so small we've had to magnify it so that you can see it more clearly. Even then it's still difficult to see. It's less than 1 millimetre across. The lens is so small it makes the microscope very difficult to use. Leeuwenhoek put the object he wanted to look at on this spike, adjusted it to about the right position, then put the microscope very close to his eye, and finally adjusted the spike so that he could see the object more clearly. As you can see, it's not very easy to use. But despite the difficulties, and despite the fact that Leeuwenhoek was one of the very first people to use a microscope, he made some remarkable discoveries. This is what he saw when he examined a scraping from inside his mouth. Today, we know the shapes he drew actually look like this. We call them bacteria. This is how Leeuwenhoek used one of his microscopes to look at living things, like fish. When he looked at the tail, he could see something like this. Blood flowing through lots of tiny capillaries. Leeuwenhoek was the first person to actually see blood flow through these small capillaries. And here's another first for Leeuwenhoek. He was the first person to see and draw sperm. He drew several different versions because he wasn't exactly sure what they looked like. They were very difficult to see. Even today, it's very difficult to see them. But with modern microscopes and cameras, we can pick out just one of them. And when you compare it with Leeuwenhoek's drawings, you can see that one of them was pretty close. Leeuwenhoek's problem was that there was a limit to the detail he could see with a single lens. To get bigger magnification, he needed lenses which were smaller and rounder. But despite his skill, do you know he could even grind grains of sand? The lenses were too small to use successfully. To get bigger magnifications, to look at small things in even more detail, other scientists used another sort of microscope. We made this model specially, and inside you can see that there's not one lens but two. One at the bottom to magnify the object, and one at the top to magnify what you see through the first lens. Microscopes with two or more lenses are called compound microscopes. And this is one of the first compound microscopes made for an Englishman called Robert Hooke. Hooke was one of the famous pioneers of the microscope, and one of his most famous drawings is this. A fly. It's a beautiful drawing, but it is only a drawing. What Hooke actually saw must have looked more like this. Hooke had great difficulty in making out all the details. And to find out why, let's do a test. We're using the same test drawing as before, with the same lens in front of it to magnify it. But this time we put in a second lens. The second lens magnifies what you see through the first lens, but it also magnifies all the faults in the first lens, with the results that the lines are surrounded by fringes. Fringes like this made it difficult for Hooke to make out clearly what he was seeing. For instance, this is what Hooke saw through his microscope when he looked at a fly's wing, and it made him think that there were blobs all over the surface. Because even at greater magnification, they still looked like blobs. He still couldn't see any more detail. But when we compare it with this modern photo of a fly's wing, we can see that the blobs are in fact tiny hairs on the wing. Modern microscopes can give much clearer photographs, even at bigger magnifications. We obtained these detailed photographs using a modern microscope like this one. It looks more complicated, but it works in the same basic way as the Hooke microscope. One lens at the top, and at the other end of the tube, another lens. However, because of the way it's made, this lens can show us more detail. The lens isn't one piece of glass, but two lenses stuck together. The double lens is called a doublet. The top lens is made from the same sort of glass that Hooke used, called crown glass, but the bottom piece is made from a special glass called flint glass. Let's see what effect the flint glass has. With the ordinary crown glass lens, our test picture's difficult to see because of the fringes. But take out the crown glass lens and put in the doublet, half of which is made of flint glass, and the fringes disappear. The only difficulty is making a lens like this. If the two pieces of glass are to fit together exactly, then the faces of each one must be made with exactly the same curve. All lenses are made in much the same way, and to make it easier for you to see what's going on, we're going to look mainly at how fairly large lenses are made. All lenses begin as a plain block of either flint glass or crown glass. This is crown glass. This machine uses diamonds to grind each side of the glass in turn. During grinding, a mixture of oil and water lubricates the lens, and a plastic skirt is wrapped around to stop the mixture flying all over the place. After grinding, the crown glass looks like this, convex on both sides. The flint glass looks like this, flat, or sometimes it can be convex on one side and concave on the other. After grinding, the new faces are very rough and you can't see through the lens. The next stages are designed to make sure the curve of the lens is correct and to smooth and polish the surfaces. First of all, the lenses are coated on one side with a special kind of wax, and then they're carefully positioned in this special tool. This is a runner. It's heated to just the right temperature before being placed on top of the lenses. The heat melts the wax. Water is used to cool the runner and so harden the wax. When everything has cooled down, the lenses are now firmly attached to the runner. The block of lenses is smoothed and polished using finer and finer grades of emery powder sprayed onto the lenses in water. From the largest to the smallest, the lenses are finely polished using a very fine powder. The polished surfaces of the lenses are tested and checked, and a similar process smooths and polishes the other surface. After the rough edges have been removed, the lenses are heated and a special glue called Canada balsam is melted onto the flint glass lens. The crown glass lens is placed on top and all the air bubbles in the glue are squeezed out. Finally, before the glue sets, the doublet is rolled to position the two lenses correctly. So that the two lenses are a perfect fit, the radius of the curve of the lenses is controlled to an accuracy of 2 to 3 thousandths of a millimetre. And now the doublet is ready to be mounted for use in a microscope. And in modern microscopes it's easy to see more details, because it's easy to put in a new lens of greater magnifying power. Here's our fly's wing again, but now through a modern lens. No distortion, no fringes. Now just a few hairs on the wing. And now just the end of the hairs, but there is a limit. At bigger magnification, the picture becomes fuzzy. Let's use our test drawing again to see what's happening. At low magnification, the drawing's clear, there's no distortion. But at bigger magnification, the details become blurred. At even bigger magnification, it becomes difficult to see the detail, until finally the detail disappears altogether. It's called empty magnification, because without the details, the magnification is useless. And even at magnifications where we can see the details, there are still problems. Here you can see the edge of the fly's wing, but the surroundings are fuzzy. If we put the surroundings in focus, then the edge becomes fuzzy. You can never see the whole picture in focus at the same time. To get improved results, modern scientists had to try a new approach. They had to make a microscope that didn't use glass lenses at all. And this is what they came up with, the very latest type of microscope, an electron microscope, which gives us pictures like this. Here's our fly again. But now the picture's clear all over. There's no fuzziness, it's easy to see and easy to work out what it is. And with the simple control, we can increase the magnification. This is part of the fly's wing we've seen before, but now magnified 2,000 times. And now 20,000 times. Part of a fly's wing magnified 20,000 times. Just one of the things made possible by the electron microscope. But today, the use of the electron microscope isn't confined to scientists in the laboratory. This is John Crossfield, an artist. He uses his electron microscope as an inspiration for his painting. Another example of someone using a tool, a microscope, to look into the world of the very small.